All right, let's look at how confidence intervals and significance tests relate to one another. Let's go back to our juicy pineapples. Okay. The mean weight of the pineapples harvested from that field was 31 ounces last year. A different irrigation system was put in. The manager wonders if the effect of the mean weight of the future pineapples grown in the field. To find out, they select and weigh a random sample of 50 of this year's crop. State an appropriate pair of hypotheses for a significance test in this setting. Be sure to define the parameter of interest. Well, we've done this already. We did this way back at the beginning. So part A, mu is the mean weight of the pineapples. Where? In this field. When? After new irrigation. What's the null and alternative? The null is nope, didn't change. There is no difference. So the null H naught is nope, still equals 31 pounds versus the alternative. The manager wants to see, did my new irrigation change the weight of my pineapples? Check the conditions for performing the test. Are we allowed to do the test? Okay, so SRS, yep, random. Independence, more than 310 pineapples in the field. Yeah, we're pretty safe there. Normality, yes, by the central limit theorem. Because n is greater than 30. Okay. A 95% confidence interval for the weight of the pineapples grown in this field is 31.255 to 32.616. Based off of this interval, what conclusion would you make? Well, is 31 in the interval? No. Therefore, we would reject the null at the 5% level. Notice 95% confidence goes with a 5% alpha for a two-sided test. 95% confidence, 5% alpha. Together, they're complementary. They make one. Right? If you think about what we're doing, it's the normal curve again. 95% in the middle, that means 5% on the outsides. If it's two-sided, that means that those 5% on the outsides equally share that 5%. All right. So what conclusion would we make about the significance test using the confidence interval? Since the null is not in the interval, we would reject the null in favor of the alternative and conclude that the pineapples are not the same weight after the new irrigation system. Part D, can we conclude that the new irrigation system caused the change in the pineapples produced? No, the only way we can talk cause and effect is through a properly designed experiment. There was no experiment here. It could have been because the weather changed this year, because the soil was better this year. Could have been for many other reasons. Since this was not a properly designed experiment, then no, we cannot talk cause and effect. Power. The power of a test is the probability the test will find convincing evidence for the null when this specific alternative is true. The power is the probability of rejecting the null when we should have rejected the null. The power of the test is directly related to the type 2 error. Okay? So the power, in order for there to be sufficient power, for the power to be good, it needs to be at least 80%. Okay. What is power? Power is just 1 minus the probability of a type 2 error. So power and type 2 error are complements of one another. Together they add up to 1. how can we increase the power? The power is super important because it's the probability of us detecting a problem when there really is one. So the power of a test is huge. There is 3 ways to affect the power. We want more power. Everybody wants more power, right? So how can we get more power in our test? Always in statistics, a good answer to make something better is have a larger sample. Okay? If the significance level alpha is larger, as alpha gets bigger, the probability of a type 1 error increases, which means the probability of a type 2 error decreases. So how can we increase power? Larger N, larger alpha, or the null and alternative are further apart. We pick an alternative that's further away from the null. The null and alternative are further away from each other, meaning it's easier to detect a difference. Okay? And really important that we know how to deal with power. Okay. All right, one last example here for this unit. The researchers in Alzheimer's experiment want to test the drug. Manufacturers claim that fewer than 10% of the patients who took its new drug for treating Alzheimer's disease will experience nausea. So they want to carry out this test given to us here. And they're doing the process for us. P is the true proportion of patients, like the ones in the study, who would experience nausea taking the new Alzheimer drug. So they're defining the parameter for us. That was nice of them. They did step 1. Earlier, we mentioned that the power of the test using a random sample of 300 patients and a significance level of 0.05 is 0.29. So they have a very small power. So they're saying here, we did all the work and we found the power is 0.29. Determine whether each of the following changes would increase or decrease the power. So if we used a smaller alpha, 0.01 instead of 0.05, would that increase or decrease power? And we said larger alpha increases power. So this smaller alpha here would decrease the power. Bigger alpha, more power. Smaller alpha, less power. If the true proportion was 0.06 instead of 0.08. So if we had a alternative further away from 0.1, it would be easier to detect a problem. Therefore, it would give us more power. So the first one, less power. Part B would give us more power. What if N was 200 instead of 300? Well, we said larger N is more power, so smaller N would be less power.